In August of 2016, astronomers announced something that stopped people mid-sentence. A planet orbiting Proxima Centauri, the closest star to Earth. The headlines wrote themselves, and they wrote themselves fast. Potentially habitable world found next door. Earth-like planet at our nearest stellar neighbour. One paper, one press release, and suddenly the most talked about piece of rock in the universe was something nobody had ever seen. The excitement was not irrational. Proxima Centauri sits just 4.2 light-years away, which in cosmic terms is essentially the house next door. Every other known exoplanet orbits a star so distant that the idea of ever reaching it, or studying it in any serious detail, belongs more to science fiction than to a funding proposal. Proxima b was different. It was close enough that future telescopes might actually read its atmosphere. Close enough that serious scientists could, with a straight face, talk about what it would take to send a probe. The distance alone made it extraordinary. Then came the other detail. The planet sat in the habitable zone around its star, the orbital band where temperatures might allow liquid water to exist on a surface. That phrase, habitable zone, landed in every article, every broadcast, every dinner table conversation where someone had seen the news. A habitable world, right there, 4 light-years away. Journalists did what journalists do. Scientists, to their credit, were more careful in their language, but the caveats got buried. The word habitable travelled fast, and it travelled without its qualifications. Within days, Proxima b had become shorthand for something enormous. Not just a planet, a candidate, a second Earth. The nearest possible place beyond our own solar system where something might be alive. It was one of those announcements that makes people look up, literally. Go find Proxima Centauri in the sky and realize you cannot see it with the naked eye, but somewhere out there, in that direction, was a world. Here is where things start to unravel. The habitable zone is not a certificate of anything, it is an energy calculation. A rough estimate of the orbital distance at which a planet receives enough starlight to keep water liquid on its surface, assuming the planet has an atmosphere. Assuming that atmosphere has roughly the right composition, assuming surface pressure is adequate, assuming a dozen other conditions that the zone concept does not measure and was never designed to measure. The habitable zone tells you one thing. The planet is not obviously too hot and not obviously too cold based on how much light it receives. That is the full extent of what it promises. Nothing more. Mars sits in our own sun's habitable zone. Mars has for billions of years. Nobody is arguing that Mars is habitable. Its atmosphere is so thin it barely registers as one. Liquid water cannot persist on its surface under those pressures. The average temperature is minus 60 degrees Celsius. The habitable zone did not protect Mars from becoming a frozen, irradiated desert, and its presence in that zone was never any guarantee that it wouldn't. The zone is a starting point for inquiry. It was never meant to be a conclusion. The scientists who announced Proxima b knew this. Their paper was careful. The language in the actual research was hedged, qualified, loaded with conditions. But a hedged scientific announcement and a global headline are two very different objects, and the headline is what most people encountered. So within days of the discovery, millions of people had absorbed a version of the story that the researchers themselves had not told. A habitable planet, right next door. The conclusion was baked in before the investigation had barely started. What followed was years of closer examination. Not one paper but dozens. Not one telescope but many, aimed at Proxima Centauri from every angle science had available. Researchers began asking not just whether the planet was in the right place, but what the planet was actually like, what the star it orbited was actually like, what the radiation environment looked like, whether an atmosphere could survive there, whether water could exist, whether anything we associate with habitability in a physical, chemical, planetary sense had any chance of persisting in that environment. The answers began coming back, and they were not encouraging. Each new study added another layer to a picture that looked less and less like the headlines of 2016. The planet had not changed. The star had not changed. What changed was the level of scrutiny, and scrutiny has a way of doing that to exciting announcements. The initial finding, the orbital detection, the mass estimate, the habitable zone placement, all of that held up. The planet is real. It is there. The orbit is confirmed. What did not hold up was the leap from those facts to anything resembling a safe assumption about what conditions on the surface might actually be. What they found, the more they looked, was a world that seemed almost designed to be hostile. To understand why Proxima b is so difficult to make work as a habitable world, you have to start with the star itself. Proxima Centauri is the closest star to Earth, 4.2 light-years away. That sounds like a meaningful distinction, something worth celebrating. The nearest stellar neighbour, practically next door in cosmic terms, but closeness is not the same as familiarity, and Proxima Centauri is not a star that resembles anything we would recognise from our own experience of the Sun. It belongs to a different category entirely. A different kind of object, running on different rules, producing a different kind of danger. Our Sun is a yellow dwarf, a G-type star. Proxima Centauri is an M-type dwarf, specifically an M5.5, which puts it near the cool, dim end of the red dwarf classification. The numbers tell the story quickly. Proxima Centauri holds about 12% of the Sun's mass. Its radius is roughly 15% of the Sun's. Its surface temperature sits at around 3042 Kelvin, compared to the Sun's 5778 Kelvin, nearly half as hot at the surface. To get a sense of what this looks like, our Sun appears white-yellow from space, blindingly bright, radiating across a wide spectrum. Proxima Centauri glows a dull, deep red, the kind of colour you might associate with a dying ember rather than a star. If you replaced our Sun with Proxima Centauri and stood at the same distance from it that Earth sits today, the sky would be dim. The star would appear much larger in the sky because you would have to be so much closer to receive any meaningful warmth. But the light itself would be thin and reddish and strange. This is the key thing to understand about the habitable zone around a red dwarf. Because Proxima burns so much cooler and dimmer than our Sun, a planet has to orbit much closer to receive enough energy to potentially keep liquid water on its surface. The habitable zone for Proxima Centauri is not where Earth sits around the Sun. It is not anywhere close. It is pulled in tight, compressed toward the star, sitting at a distance of about 0.048 astronomical units. For reference, Mercury, the innermost planet in our solar system, orbits the Sun at about 0.39 astronomical units. Proxima b orbits its star at roughly 1/8 of Mercury's distance from our Sun. That is how close you have to get to a star this dim just to stay warm. That proximity is the first clue that something is going to go wrong. At such close range, the star's gravity exerts tremendous tidal forces on the planet, attempting to lock it into synchronous rotation, where one side perpetually faces the star and the other plunges into permanent darkness. This creates temperature differentials between the scorched day side and the frozen night side that dwarf anything in our solar system. The atmospheric circulation patterns would be chaotic and extreme. The planet experiences the full brunt of stellar radiation without the protective buffer of distance that Earth enjoys. These consequences alone would present formidable obstacles to habitability. But before we get to what proximity means for the planet, it is worth pausing on what kind of star is sitting at the centre of that orbit. Because Proxima Centauri is not simply a smaller, cooler, quieter version of the Sun. That assumption, a cooler star equals a calmer star, turns out to be one of the more consequential mistakes in how people first thought about red dwarf planets. Red dwarfs are, in many respects, magnetically overactive. Our Sun generates a magnetic field through a process driven by its internal rotation and the movement of plasma through its interior. That field fluctuates on an 11-year cycle. It produces solar flares and occasionally large events. But the Sun is, by the standards of stars in our galaxy, relatively well behaved. Red dwarfs like Proxima Centauri have a different internal structure. They are fully convective, meaning the plasma inside them churns all the way from the core to the surface, rather than existing in separate layered zones the way our Sun does. Full convection produces a tangled, chaotic, intensely active magnetic field. The field doesn't settle into orderly patterns. It generates constant activity, constant eruptions, constant releases of energy at the surface. Proxima Centauri has been watched carefully. Astronomers have monitored it for flares, for magnetic activity, for the kind of energetic events that pour out of active stars. What they found was not occasional turbulence. The star produces flares at a rate and intensity that is, by comparison to our Sun, extraordinary. More on those specific numbers shortly. But even before you get to the dramatic events, the baseline magnetic behavior of this star is aggressive in a way that matters enormously for anything orbiting it at close range. There is also the question of size and what it implies. Small stars live a long time. Our Sun has a lifespan of roughly 10 billion years total. Proxima Centauri, because it burns through fuel so slowly and efficiently, has an estimated lifespan on the order of 4 trillion years. The universe itself is only about 13.8 billion years old. Proxima Centauri is not approaching old age, it is barely getting started, and young, magnetically active red dwarfs are not gentle objects. They are volatile, prone to enormous energetic outbursts, running magnetic cycles that bear no resemblance to the relatively predictable behavior of a mature, massive star. What this means for any planet in the habitable zone is that the calm the star's dimness might suggest is an illusion. Proxima Centauri does not produce the intense heat our Sun does. It does not bathe its nearby planet in the same quantity of visible light. But in terms of magnetic violence, in terms of high-energy radiation, in terms of the raw disruptive activity pouring out of its surface, it is not a docile object. The very features that make it seem like a friendly candidate for hosting a habitable planet, its small size and cool surface, are connected to the features that make it one of the more hostile stellar environments in the neighbourhood. The habitable zone is close because the star is dim. But dim does not mean quiet. It never meant quiet. Proxima Centauri is not a quiet old star sitting peacefully in the dark. It is one of the most magnetically aggressive objects in the neighbourhood. Before you even get to flares, before anything dramatic happens, Proxima b has a baseline radiation problem. This is the part that gets lost in the headline version of the story. People hear about solar flares and superflares and picture dramatic explosive events, a star suddenly erupting and blasting its planet. That picture is real, and we'll get to it. But underneath the drama, before any flare fires at all, there is a quieter problem that is arguably more fundamental. Proxima Centauri, on a calm and ordinary day, with nothing exceptional happening, is already bathing its nearest planet in a radiation environment that Earth has never experienced and could not survive unchanged. The measurement that captures this is a single number. The top of atmosphere XUV irradiance at Proxima b is roughly 0.293 watts per square metre. That sounds abstract until you put it next to the Earth equivalent. Our planet receives about 60 times less. 60 times. Not 10% more, not double, not even 10 times. The baseline, the floor, the minimum radiation level on a day when Proxima is doing nothing unusual sits 60 times higher than what Earth's upper atmosphere handles from our own Sun. To understand why that number matters so much, you need to know what XUV radiation actually does when it hits a planet. XUV stands for X-ray and extreme ultraviolet. Wavelengths far shorter and more energetic than the ordinary visible and infrared light that warms a planet's surface. Ordinary sunlight carries heat. XUV radiation does something different. When it reaches the upper layers of an atmosphere, it doesn't gently warm the surface below, it tears into the gas molecules themselves. It strips electrons away from atoms, a process called ionization, converting neutral gas into plasma, and ionized gas at high altitude behaves in ways that neutral gas doesn't. It heats up sharply, it expands, and when it expands far enough, fast enough, it escapes. This process is called atmospheric escape, or more specifically, thermal escape, driven by photoionization, and it is the mechanism by which planets lose their atmospheres to space. Not in dramatic bursts, not visibly, but steadily, molecule by molecule, over geological time. Earth loses a small amount of atmosphere this way from our own sun. It's slow enough, and our star gentle enough, that the loss rate over Earth's history has been manageable. Life got billions of years to develop because the atmosphere stayed thick enough to matter. Proxima b faces a version of this process that is categorically different in scale. With 60 times the XUV input hammering the upper atmosphere, the heating, the ionization, and the resulting escape rate are not 60 times worse, because the physics doesn't scale linearly. In some models they are far worse. The upper atmosphere on Proxima b, assuming one exists, would be perpetually energized at a level that Earth's thermosphere only approaches during the most intense solar storms. On Earth, those storms are temporary. They last hours or days, and then the upper atmosphere cools and resets. On Proxima b, that is the resting state. Now bring in what this means for the ozone layer specifically, because the ozone story and the XUV story are deeply connected. Earth's ozone layer sits in the stratosphere and absorbs ultraviolet radiation in a narrower wavelength band, protecting the surface below. It works because our sun is relatively gentle in those wavelengths. The ozone formed over billions of years and has remained stable enough to persist because the destruction rate from solar UV never permanently overwhelmed the formation rate from oxygen photochemistry. It is a dynamic balance, and it is a fragile one. Even the chemistry of human-made refrigerants managed to tip that balance enough to create a hole over Antarctica. On Proxima b, the incoming radiation at the relevant wavelengths doesn't just challenge that balance, it overwhelms it by an order of magnitude before a single flare fires. The ordinary, unremarkable XUV flux from Proxima Centauri is enough to drive ozone destruction rates that no plausible formation chemistry could keep up with. Ozone needs time to assemble. It needs a relatively quiet environment to persist. Proxima b, on its quietest day, provides neither. There is another layer to this that is easy to miss. XUV radiation doesn't just attack an ozone layer that already exists. It attacks the precursors. It dissociates the oxygen molecules that ozone is built from. It energizes the upper atmosphere enough to allow those lighter molecules to escape before they can cycle back into protective chemistry. The attack is not just on the shield, it is on the raw materials the shield would be built from. It energizes the upper atmosphere enough to allow those lighter molecules to escape before they can cycle back into protective chemistry. The attack is not just on the shield, it is on the raw materials the shield would be built from. An ozone layer on Proxima b would be trying to form inside a machine designed to prevent it. Compare Earth's situation more carefully, and the gap becomes clearer. Our planet has had roughly 4 billion years of relatively stable conditions under a star that, while it has had active periods, has never subjected us to anything like the baseline Proxima delivers. Over that time, the atmosphere thickened, the ozone layer stabilized, liquid water stayed liquid, and life had room to evolve from single cells to complex organisms. The slow accumulation of conditions was possible because the radiation environment, while not trivial, was survivable for chemistry. Proxima b, sitting at 0.048 astronomical units from its star, receives this radiation with almost no buffer. Distance matters enormously. Earth sits at 1 astronomical unit from the Sun. Proxima b is 20 times closer to its star. Radiation intensity falls off with the square of distance, so even if Proxima were identical to the Sun in its XUV output, the planet would receive 400 times more simply from being that close. Proxima is not identical to the Sun in its XUV output. It is dramatically more active per unit of total luminosity than the Sun is. The two factors compound each other. The closeness and the activity combine to produce a radiation environment that has no analogue in our solar system. This is not a situation where you add more sunscreen. Sunscreen blocks UV from reaching your skin. It does not prevent the upper atmosphere from being stripped away over 1 billion years. The scale of what Proxima b faces is not a survivability challenge for organisms on a surface. It is a structural threat to the planet's ability to hold on to its atmosphere at all. Every molecule that escapes is one that cannot contribute to surface pressure, to radiation shielding, to the greenhouse warmth that would keep any water liquid. And all of this is the baseline, the quiet version, the ordinary between-events condition on a day when Proxima Centauri is simply existing, not doing anything remarkable. The quiet days, the ordinary days between eruptions, are already doing damage that compounds over millions of years. The flare record for Proxima Centauri is one of those datasets where the more carefully you look at it, the worse things get. A team of astronomers pointed the Everyscope telescope array at Proxima Centauri and just watched. For 1,344 hours, spread across just over 2 years, they tracked the star's brightness with enough precision to catch individual eruption events. What they logged was not a handful of anomalies. In that window, they detected 24 large flares, not small fluctuations, not noise in the data, large eruptions, each releasing between 10 to the 30.5 and 10 to the 32.4 ergs of energy. The numbers sound abstract until you try to put them next to something real. The most powerful nuclear weapon ever detonated by humanity released roughly 10 to the 25 ergs. A single one of these ordinary large flares from Proxima Centauri outpaces that by a factor of tens of millions. These are not extraordinary events in the Proxima Centauri catalogue. These are the routine ones. Then the researchers did the math on the bigger events. If you correct for the fact that the star was only being watched for a fraction of each year, the statistics point towards something uncomfortable. Superflares. Events reaching 10 to the 33 ergs, 10 times more powerful than the largest eruptions directly observed, are likely happening at least 5 times annually. 5 times every year with almost clockwork regularity, not occasionally, not once in a generation. 5 times a year, and that is a floor estimate, not a ceiling. To understand why this matters, you have to understand what 10 to the 33 ergs actually represents. Our Sun produces flares regularly, even significant solar flares, the kind that disrupt satellite communications and cause power grid failures here on Earth, typically release around 10 to the 32 ergs at their most intense. The Carrington event of 1859, the most powerful solar storm in modern recorded history, the one that set telegraph wires on fire and produced auroras visible from the Caribbean, is estimated at somewhere in that range. That event happens perhaps once per century on our Sun. Proxima Centauri produces something 10 times more powerful than that, 5 times per year, every year. Here is something worth sitting with for a moment. The Carrington event is still discussed today as a cautionary tale about what the Sun is capable of. Scientists write papers about what would happen if it hit us today. Governments consider it a low-probability catastrophic risk. It is the kind of thing that gets treated as a once-in-civilization event. For Proxima b, something worse than that is not a rare disaster. It is the seasonal schedule. The energy difference between a strong solar flare and a Proxima superflare is not a small step up. It is an order of magnitude, and orders of magnitude in stellar physics are not gradual transitions. They represent categorically different physical regimes. When a superflare at 10 to the 33 ergs erupts from Proxima Centauri, it floods the surrounding space with X-rays, extreme ultraviolet radiation and high-energy charged particles in quantities that overwhelm any straightforward comparison to solar activity. The wave of radiation crosses the distance between Proxima and its planet in minutes. There is no warning in any useful sense. By the time the light from the flare's brightening reaches the surface of Proxima b, the radiation is already arriving. Compare this to the Sun's behavior, and the contrast becomes even sharper. Astronomers have studied solar flare records going back decades using satellite data, and centuries using historical accounts. True superflares from our Sun, events at 10 to the 33 ergs or above, are rare enough that there are no confirmed examples in human history. Some researchers think they may occur on timescales of thousands of years. Others think they may have happened once or twice in the last 10 millennia. The statistical records are thin because the events are so uncommon. When scientists model what a true solar superflare would do to Earth, the results are alarming enough that the scenario is treated as a serious existential risk. The consequences modelled include widespread ozone destruction, satellite loss, and long-term disruption to global infrastructure. All of that from an event our Sun might produce once every several thousand years. Proxima Centauri produces it 5 times annually. The Everyscope dataset captured this in a time window short enough to make the frequency undeniable. 1,344 hours is not a long survey in astronomical terms. It is 56 days of continuous observations spread across just over 2 years. Within that narrow slice of time, 24 large flares showed up, and behind those 24 events, the statistics implied the larger eruptions were happening with disturbing regularity off-camera in the windows when the telescope was pointed elsewhere or when observations were unavailable. The 24 detected flares are not the whole picture. They are just the portion that happened to land in the monitoring window. This changes the framing entirely. When you hear about a planet orbiting in a habitable zone and the word habitable triggers associations with Earth, there is an implicit assumption buried in that comparison. The assumption is that the star behaves roughly like our star, but it has quiet periods and active periods, that major events are exceptional, that the baseline environment is stable enough for chemistry to develop slowly over billions of years. Proxima Centauri violates that assumption at every level. There are no real quiet periods, but 24 large flares in 1,344 hours means the star was producing a significant eruption roughly every 56 hours during the observation window. Every 2 days, something notable was happening, and 5 times each year, something catastrophic. What this does to a planet in the habitable zone is not simply a matter of surface conditions getting harsh during flare events. The cumulative effect is the issue. Each superflare strips material from the upper atmosphere. Each one delivers a pulse of ionizing radiation, powerful enough to heat the thermosphere dramatically and drive additional atmospheric escape. Each one damages whatever ozone chemistry might be trying to maintain itself. None of these effects fully reverse in the days between events. The planet is not recovering from one flare before the next significant eruption arrives. The damage accumulates faster than any natural process can repair it. Think of it like this. A building that catches fire once and is then repaired can survive. A building that catches fire 5 times per year never finishes rebuilding between events. Eventually, the question is not whether the structure survives the next fire. The question is whether there is any structure left to burn. Proxima b's atmosphere, if it has one, faces something structurally similar. Repeated high-energy events on a timeline that allows no meaningful recovery. The flare problem and the baseline radiation problem described earlier are not 2 separate issues adding together politely. They compound each other. The baseline XUV irradiance is already stripping atmospheric gas continuously. The flares arrive on top of that constant erosion and drive additional losses in bursts. Between the steady drain and the periodic catastrophic pulses, the planet's atmosphere is being worked on from both directions simultaneously. There is no safe gap in the timeline. There is no century of calm during which the atmosphere thickens and stabilizes, and the surface chemistry finds its footing. The assault is continuous, and 5 times each year it escalates dramatically. Our Sun has bad days, Proxima Centauri has bad years, and they never stop. There is a bacterium called Deinococcus radiodurans that was first discovered living inside the cooling pools of a nuclear reactor. Not near the reactor, not in the building next door, inside the cooling water itself, where radiation levels were high enough to kill almost anything else on the planet. Scientists who first found it in the 1950s assumed it was a contaminant. They ran the tests again. The bacterium was still there, still alive, still multiplying in conditions that should have been fatal several times over. The nickname it eventually earned was Conan the Bacterium. That tells you something. This organism survives radiation doses thousands of times higher than the dose that would kill a human being. It does this through a repair mechanism so efficient it can reassemble its own genome after it has been shattered into hundreds of fragments. The DNA gets torn apart, the bacterium stitches it back together, then it keeps going. It has been tested in simulated Mars conditions. It has survived desiccation, cold, acid, and vacuum. Of every organism discovered on Earth, Deinococcus radiodurans is the one scientists reach for when they want to know where the hard limit of biological survival actually sits. If you are building a mental picture of what life on an extreme world might look like, this is the organism you start with. This is your baseline. So here is the question worth sitting with. If you place Deinococcus radiodurans on the surface of Proxima b during a superflare, what would happen to it? The answer came out of research calculating the actual UV dose that would reach an unshielded surface during one of these events. The number is not ambiguous. During a Proxima superflare, the UV dose hitting the surface would be 65 times larger than the dose required to kill 90% of the most radiation-resistant organism on Earth. Not 65% more, 65 times more. The organism that survives nuclear reactor cooling pools, the one that reassembles its shattered genome and keeps dividing, would be killed comprehensively. During a single flare event from a star 4 light-years away, let that number sit for a moment. 65 times the lethal dose for Conan the Bacterium. This is not a margin of difficulty. It is not a challenging environment that might push evolution in interesting directions. It is a number that places surface life during a flare event outside the range of what biology, as we understand it, can accommodate. The gap between what Deinococcus radiodurans can handle and what a Proxima superflare delivers is not a crack to squeeze through, it is a canyon. Now remember what the previous section established about how often these flares happen. 5 superflares per year, statistically, every year, not occasionally, not once in a geologic era, repeatedly, regularly, on a timescale that is short even by human standards. Each one of those events produces a UV bombardment 65 times past the breaking point of the toughest thing biology has ever produced. Any organism sitting on the surface of Proxima b would not simply struggle, it would be gone. This has implications that go beyond one particularly tough bacterium. Deinococcus radiodurans is not standing in for a specific niche of life. It is standing in for the concept of a ceiling. If the hardiest organism we know of is killed 65 times over by a single event, every other form of surface life we can imagine falls somewhere below that ceiling. Complex organisms, multicellular life, anything with exposed tissue and a metabolism built around the assumption of a relatively stable radiation environment, would face the same problem in more immediate form. The flare does not discriminate between the tough and the fragile. It simply delivers a dose that exceeds the upper limit of biological tolerance for anything we have ever studied. The obvious response to this is to go underground. Water and rock both absorb radiation. Enough of either provides effective shielding. Deep ocean environments on Earth are home to entire ecosystems that never see sunlight. Life that runs entirely on chemical energy from hydrothermal vents. If Proxima b has liquid water, something might survive at depth. If the planet has a rocky crust, organisms far enough below the surface might never feel the flares at all. This is true, as far as it goes, and it is probably the most honest version of a hopeful argument for life on Proxima b. But it comes with a set of its own complications that deserve to be named directly. First, subsurface or deep ocean life requires that the subsurface or deep ocean exist. Whether Proxima b has liquid water in any form depends on its atmosphere, its pressure, its temperature distribution, and a long list of other unknowns that nobody has resolved. Second, even if liquid water exists somewhere on the planet, the flares are not just a surface problem. The high-energy radiation from a superflare interacts with the atmosphere and drives processes that can affect the chemistry of the entire planet over time. Third, and perhaps most importantly, life that retreats permanently underground or to the deep ocean is life that cannot meaningfully spread, cannot reach the surface, cannot participate in the kind of planetary-scale cycling of elements and energy that characterizes life on Earth. It is sequestered, hidden, surviving perhaps, but not thriving in any sense that would leave a detectable signature from 4 light-years away. There is also the question of how life gets underground in the first place. On Earth, subsurface life largely descended from surface life. The ancestors of deep rock bacteria were surface organisms that gradually colonized downward. If the surface of Proxima b was sterilized during early superflare events, before complex chemistry had time to take hold, the pipeline from surface to subsurface may never have been established. Life needs a starting point. Superflares happening 5 times a year would have been happening during the early history of the planet too, possibly more frequently, given that young red dwarfs are even more magnetically violent than older ones. The window for life to get a foothold on the surface, build complexity, and then retreat downward may never have opened. None of this is a proof that Proxima b is lifeless. Science does not work by ruling things out with certainty from this distance. What the 65 times number does is set the terms of the problem clearly. Surviving on the surface during a flare is not a question of adaptation at the edges. It is a question of whether any biology we understand can exist at all under those conditions. The answer is no, and the flares come 5 times a year, every year, with a regularity that leaves no room for recovery between events. The planet doesn't need to be uninhabitable all the time for life to be impossible. It just needs to be fatal often enough. Here is the cruelest part of the flare problem. It is not the flares themselves. It is what happens after them, in the long quiet spaces between them, when you might expect the planet to have a chance to recover. It doesn't. And the reason it doesn't comes down to a single molecule that most people never think about until it's gone. Ozone. 3 oxygen atoms bonded together in a layer high in the upper atmosphere. On Earth, that layer sits roughly 15 to 35 kilometers above the surface, thin enough that if you compressed it down to sea level pressure, it would only be about 3 millimeters thick. 3 millimeters standing between surface life and the full intensity of ultraviolet radiation from the sun. It sounds almost comically fragile, but it has held for hundreds of millions of years, and because of it, life moved out of the oceans and onto the land. Without that layer, the surface of Earth would look very different. Nothing with exposed DNA would last long in open sunlight. The ozone layer is not a nice feature of our atmosphere. It is the reason the surface is biologically available at all. Now consider what a superflare does to it. When a massive burst of high-energy radiation and charged particles hits the upper atmosphere, it drives chemical reactions that break ozone molecules apart faster than they can reform. Nitrogen oxides flood the stratosphere during these events, and nitrogen oxides are ozone's chemical enemy. They catalyze the destruction of ozone in cascading chain reactions that keep running long after the flare itself has ended. The flare might last minutes or hours. The chemistry it sets in motion keeps destroying ozone for months. Studies of what large solar proton events do to Earth's ozone layer give a sense of the scale. A significant event on our relatively calm sun can knock out measurable fractions of polar ozone. What a Proxima superflare delivers is orders of magnitude more energetic than anything our Sun produces in a typical cycle. After one of these events, ozone begins rebuilding. The same sunlight that helps destroy ozone also drives the photochemical reactions that create it. Given enough time without another major disruption, the layer can recover. The critical phrase there is enough time. On Earth, recovering from a significant ozone depletion event takes years. The estimates for recovery after a Proxima-scale superflare land in the same range, multiple years of gradual chemical reconstruction before the layer approaches its original density. Here is where the math turns brutal. Proxima Centauri produces superflares at the energy level capable of stripping ozone occasionally not once a decade, but roughly 5 times per year or more, based on the Everyscope monitoring data. 5 events per year, recovery time measured in years per event. The planet would be hit again before the atmosphere had finished healing from the last time, and then again before it healed from that. The ozone layer would not be a permanently depleted shield, degraded but still present. It would be continuously redestroyed before any meaningful recovery could happen. The concept of an ozone layer as something that builds up and persists becomes essentially incoherent in this environment. This is the part that separates the ozone problem from the raw radiation problem described in the section before this one. The previous picture was about intensity. That baseline XUV irradiance on Proxima b is already 60 times higher than what Earth receives on ordinary quiet days before anything dramatic happens. That is a problem of degree. The ozone problem is a problem of permanence. It is not asking whether a shield can handle more punishment than it was built for. It is asking whether a shield can exist at all when the events that destroy it arrive faster than the physics of chemistry can rebuild it. The answer, under these conditions, is almost certainly no. Some researchers have looked at whether different atmospheric compositions could compensate. A dense atmosphere of carbon dioxide and nitrogen, for example, can absorb some damaging ultraviolet wavelengths even without ozone, provided the surface pressure is high enough and the atmospheric column is thick enough. That is not nothing. Under certain favourable assumptions about composition and pressure, some protection persists. But those results come with conditions attached. They assume an atmosphere heavy and thick enough to provide that coverage. An atmosphere whose existence on Proxima b is itself deeply uncertain, for reasons the earlier sections have already laid out. And they assume protection against the UV wavelengths those specific molecular absorbers happen to target. The range of damaging radiation from a superflare is not narrow. It covers frequencies that carbon dioxide and nitrogen do not handle the way ozone does. There is also the question of what continuous disruption does to the chemistry of the upper atmosphere over long timescales. It is not just that ozone fails to rebuild. The same energetic events that strip ozone are loading the stratosphere with reactive chemical species that interfere with other atmospheric processes. Each superflare is not a reset to some neutral baseline. It is an addition to an accumulating chemical environment shaped by the previous 5 events and the 5 before those, in a star system that has been producing flares at this rate for billions of years. Whatever the atmosphere of Proxima b looks like today, it has been chemically shaped by an assault that has never let up. And so you arrive at the surface conditions during a flare event on a planet without a functioning ozone layer. The previous section put numbers on what a single superflare does to Demococcus radiodurans, the most radiation-resistant organism known on Earth. 65 times the dose needed to kill 90% of it. That number assumed no ozone shielding. It assumed direct exposure. For Proxima b, no ozone shielding is not a worst-case assumption. It is the expected condition. There is no buffer. Every superflare hits the surface at full intensity. The organism that survives nuclear reactor cooling pools does not survive it. Nothing on the surface does. It is not that the shield gets damaged. It is that the shield never gets a chance to exist in the first place. The flares are the dramatic version of the problem, the kind that gets headlines. A superflare erupts, the sky goes white, the numbers are staggering, and the story writes itself. But there is another layer to what Proxima Centauri does to its planet, and it operates not in bursts but continuously, around the clock every single day. It has nothing to do with flares. It is the stellar wind, and in some ways it is the more quietly devastating of the two problems. Every star streams charged particles outward in all directions. Our Sun does it constantly. This flow of protons, electrons, and heavier ions radiates outward through the solar system and eventually fades into interstellar space. Earth sits inside this stream. What protects us is the planet's magnetic field, an invisible shell generated by the churning of molten iron in our core. The magnetic field pushes back against the solar wind, deflecting particles around the planet rather than letting them hammer directly into the atmosphere. The boundary where the magnetic pressure and the solar wind pressure balance each other has a name: the magnetopause. For Earth, this boundary sits roughly 10 Earth radii out from the surface. The solar wind presses in, the magnetic field presses back, and the standoff holds. The atmosphere beneath stays intact. Proxima b does not have that luxury. The stellar wind from Proxima Centauri hits the planet at pressures more than 2,000 times what Earth experiences. 2,000 times. To put that in physical terms, imagine the weight of the solar wind pressing against Earth's magnetic shield. Then multiply that force by 2,000. Studies using magnetohydrodynamic simulations, detailed models of how magnetic fields and plasma interact, push the number even further in peak conditions. Some of those models find stellar wind pressures 4 orders of magnitude above Earth's baseline. That is 10,000 times greater. During active periods, the planet is being hit by something closer to a sustained blast than a breeze. What this does to the magnetopause is where things become particularly unstable. On Earth, that boundary is relatively steady. The solar wind varies and the magnetopause shifts accordingly. But the variation is modest. The boundary stays roughly where it is. On Proxima b, the models tell a different story. The stellar wind pressure fluctuates wildly on timescales as short as a single day. The magnetopause standoff distance, the point where any magnetic field Proxima b might have, would balance the incoming pressure, shifts by factors of 2 to 5 within 24 hours. Think about what that means physically. The boundary of the planet's magnetic shield is not a stable wall. It is something closer to a membrane breathing in and out, rapidly every day, compressed dramatically by surges in the stellar wind, and then expanding again when the pressure briefly drops. A magnetosphere that behaves this way is not functioning as a coherent shield. It is lurching between states, and each inward compression brings the boundary closer to the atmosphere, exposing more of the upper layers to direct particle bombardment. This fluctuation has consequences that compound over time. Every time the magnetopause is pushed inward, a larger portion of the upper atmosphere sits outside whatever magnetic protection exists. Charged particles get access to atmospheric gas they would otherwise be deflected around. They interact with molecules in the upper layers, heating and ionizing them. Gas that is heated enough begins to escape. It reaches escape velocity and flows out into space. This process, called atmospheric sputtering and ion escape, is not hypothetical. It happened on Mars. Mars once had a thicker atmosphere and likely had liquid water on its surface. It lost both over billions of years as its magnetic field weakened, and the solar wind gradually stripped the atmosphere away. Mars is the slow version of this story. Proxima b is facing a pressure environment roughly 1,000 times more intense than what finished Mars off. Now consider the worst case. All of the above assumes Proxima b actually has a magnetic field in the first place. That assumption is unverified. We have no direct measurement of the planet's magnetic properties. Whether it generates a protective field like Earth's depends on its interior. Specifically, whether it has the right kind of liquid metallic layer churning with enough convective motion to sustain a dynamo. That is not guaranteed. Rocky planets do not automatically have strong magnetic fields. Mars lost its dynamo early. Venus has essentially no global magnetic field. Mercury's is weak. If Proxima b is in the same category, the stellar wind hits the atmosphere directly with nothing in between. The numbers in that scenario are severe. Ion escape rates for an unmagnetized planet at Proxima b's position would be roughly 100 times higher than the ion escape rates observed on any terrestrial planet in our solar system. 100 times higher than Mars at its worst. 100 times higher than Venus, which is already losing atmosphere at a measurable rate despite sitting at a far more forgiving distance from a far calmer star. The unmagnetized version of Proxima b is not a planet slowly losing its atmosphere at a pace that, over 1 billion years, would strip enormous quantities of gas into space. Even in the more optimistic scenario, where Proxima b does have a magnetic field comparable in strength to Earth's, the same simulations show that ion escape rates are still higher than those observed on any planet in our solar system. The best case is not as good as Earth's worst case. The magnetic field helps, but it does not bring the situation into a range we would consider normal or safe. The stellar wind at this distance is simply too intense, and the fluctuations too rapid for any Earth-like magnetosphere to fully contain. There is something worth holding in your mind here. The flares come in discrete events. They are devastating, but they are also punctuated by intervals between them. The stellar wind does not work that way. It presses in constantly, varying in intensity but never stopping. The pressure during a quiet period between flares is still 2,000 times what Earth sits inside. Every hour of every day, the planet's magnetosphere, if it has one, is being compressed, stretched and destabilized by a stream of particles that dwarfs anything our solar system's terrestrial planets have to deal with. The atmosphere, if one exists, is being slowly bled away at the top. The ions that escape do not come back. The stellar wind problem does not produce a moment of crisis the way a superflare does. There is no event, no peak, no headline. It simply never lets up. The steady pressure, the relentless daily assault of charged particles, is in some ways harder to survive than the spectacular events. Proxima b orbits so close to its star that it is almost certainly frozen in place. Not frozen in temperature, though that comes later. Frozen in rotation. Locked. The same face pointed at Proxima Centauri forever. The same face pointed away from it forever, with no sunrise and no sunset anywhere on the planet. Ever. To understand how this happens, you have to think about gravity at close range. When a planet orbits far from its star, the gravitational pull on the near side and the far side are roughly similar. The difference is small enough that the planet can spin freely. But move the planet very close in, and that difference starts to matter. The star's gravity tugs harder on the near side than on the far side, and that uneven pull creates a torque. Over time, that torque acts like a brake. It gradually slows the planet's rotation until the spin rate matches the orbital period exactly. 1 rotation per orbit. The planet stops turning relative to its star, and from that point on, one hemisphere stares into that red glow without ever looking away. This is the same process that locked our moon to Earth. The moon always shows us the same face. It rotates once per orbit, which is why we never see the lunar far side from the surface of Earth. Proxima b is in the same situation, except the object doing the locking is a star, not a planet, and the consequences of that lock are not just astronomical curiosities. They define every physical condition on the world. At 0.048 astronomical units from Proxima Centauri, Proxima b sits about 8 times closer to its star than Mercury sits to our Sun. At that distance, the locking timescale works out to roughly 10,000 years. 10,000 years sounds long until you remember that the Proxima system is billions of years old. 10,000 years is nothing. It is a rounding error in geological time. This planet would have been locked in place within the first fraction of a percent of its existence, long before anything resembling life could have had time to get started. Whatever Proxima b is today, it has been this way essentially since it formed. Now picture what that actually means on the ground. The day side of the planet receives constant unbroken stellar radiation. There is no night. The star hangs in exactly the same position in the sky, hour after hour, year after year, millennium after millennium. Temperatures on this hemisphere can reach up to around 40 degrees Celsius. That sounds manageable, almost tropical, but keep in mind that this heat has nowhere to go through the ordinary cycling of day and night. It just accumulates. Whatever atmosphere might exist is being baked on this side continuously, with no relief. If you stood there, the star would be a small, dim red disk fixed in the sky above you, not rising, not setting, not moving by even a fraction of a degree over the course of your entire lifetime. Turn around and face the other way, and you are looking toward a horizon that leads to permanent night. Cross that horizon and you enter a world that has not seen starlight in billions of years. The night side of Proxima b sits in total, unbroken darkness, radiating whatever heat it has out into space with nothing coming back to replace it. Temperatures there drop to around negative 123 degrees Celsius. For comparison, the coldest naturally occurring temperature ever recorded on Earth's surface is around negative 89 degrees Celsius, at the center of Antarctica. The permanent night side of Proxima b is roughly 34 degrees colder than the worst place our planet has ever produced. It is not a cold night, it is a cold eternity. This is not a seasonal extreme. It is not a polar region. There is no summer coming. If you were on the night side, every single direction you looked would lead toward more darkness. The only way to reach light would be to walk to the terminator, the line dividing the two hemispheres, and that line does not move. It sits in the same place on the planet's surface forever, a fixed boundary between fire and ice. Some researchers have pointed out that Proxima b might not be in a perfect one-to-one lock. If the planet's orbit carries enough eccentricity, gravitational dynamics could push it into a 3-to-2 spin-orbit resonance instead. Mercury is the classic example of this in our own solar system. Mercury completes 3 rotations around its own axis for every 2 trips around the Sun. A planet in this state does rotate technically, but slowly. For Proxima b, given that its orbital period is 11.2 Earth days, a 3-to-2 resonance would produce a day length of around 7.5 Earth days. That is 7.5 days of continuous daylight followed by 7.5 days of darkness. This is better than permanent lock, but it is not remotely like anything on Earth. Temperature swings across that kind of day-night cycle would be extreme. The day side would heat up enormously over more than a week of ectoradiation. Then the night side would plunge into brutal cold before the next rotation brought the Sun back around. Whether the planet even ends up in this resonance depends on its orbital eccentricity, and that is an open question. Additional planets in the system and gravitational interactions with the broader stellar neighborhood could push the orbit in either direction. Even in the more favorable 3-to-2 scenario, the conditions on Proxima b remain extraordinarily harsh compared to Earth. A week-long day on a world this close to an active flare star is not an improvement that changes the fundamental picture. It is a slightly different version of the same problem. What both scenarios share is this: a world with no stable, moderate temperature across any large fraction of its surface, no broad temperate zone, no planetary scale spring or autumn. The temperature difference between the two hemispheres in full tidal lock is not a gradient that life could gradually adapt to by moving poleward or equatorward. It is a cliff. You are either on the side that bakes or the side that freezes, and the cliff between them is permanent. There is one narrow exception. Right at the boundary between the day and night hemispheres, along the terminator line, neither extreme fully dominates. Temperatures in this ring might hover somewhere between the burning and the frozen. Atmospheric circulation, if the planet has an atmosphere, could carry warm air from the day side into this zone and cold air from the night side back across. Ocean currents, if there are oceans, could do something similar with water. Models suggest that this twilight band could potentially support temperatures somewhere between -30 and +30 degrees Celsius, depending heavily on atmospheric thickness, composition, and circulation patterns. It is a narrow ring of perpetual red-tinged dusk, with the star sitting just at the horizon and never going, anywhere. The only zone where temperatures might support liquid water is a ring of perpetual twilight at the boundary between eternal day and eternal night, and even that depends on everything else going right. Everything said so far about what might protect Proxima b or fail to protect it rests on a single assumption that nobody has verified. There is an atmosphere. That is it. That is the assumption. Every calculation about surface temperatures, every model of UV shielding, every scenario where a twilight zone stays warm enough for liquid water, all of it starts from the premise that something is sitting between the planet's surface and the star above it. And no telescope has confirmed that anything is there. This is not a minor gap in the data, it is the central gap. When researchers model what the radiation environment looks like at the surface of Proxima b, they are modeling what reaches the ground after passing through an atmosphere they have not seen. When scientists calculate whether ozone could form and persist, they are calculating the fate of a layer inside an atmosphere whose existence is unconfirmed. The entire architecture of the habitability conversation rests on a foundation that has never been directly observed. That is not a criticism of the science. It is simply the honest description of where things stand. No telescope operating today can directly measure the atmosphere of Proxima b. The planet does not transit its star from Earth's viewing angle in a way that would let astronomers capture starlight filtered through its upper atmosphere, which is the standard method for reading what a distant planet's air is made of. Direct imaging at this scale and separation is beyond current instruments. So everything said about the atmosphere, its pressure, its composition, whether it has water vapor or carbon dioxide or nitrogen or anything at all, is inference. It is modeling built on assumptions, not measurement built on observation. Here is why this matters more than it might seem. Consider the radiation environment discussed earlier. The extreme ultraviolet flux hitting Proxima b is roughly 60 times what Earth receives. Superflares pound the planet multiple times per year. Stellar wind pressures are orders of magnitude beyond anything in our solar system. All of those numbers describe what arrives at the top of whatever atmosphere exists. But if the atmosphere is thin, really thin, a fraction of Earth's surface pressure, then the protection those numbers account for collapses almost entirely. The difference between a thick atmosphere and a thin one is not a mild adjustment in the surface conditions. It is the difference between a planet that might marginally function and a planet that is simply exposed. The early history of Proxima b makes the atmosphere question much harder. Proxima Centauri is an old star now, relatively speaking, magnetically violent but settled into something like a routine. It was not always this way. Young red dwarf stars go through a pre-main sequence phase that can last hundreds of millions of years, during which they are significantly more luminous and far more aggressive. During that phase, Proxima would have been pouring out radiation and stellar wind at levels that dwarf even what the planet endures today. Any primordial atmosphere that accumulated during planetary formation, hydrogen, helium, early volatiles from accreting material, would have been subjected to extraordinary irradiation from the very beginning. The most likely outcome is that it was stripped away entirely before the planet was even 1 billion years old. This is not a speculative worst case. It is closer to the expected outcome given what is known about how red dwarfs evolve. The greenhouse gases that might have offered early protection, whatever water existed on or near the surface, the models suggest they could have been wiped out during this violent early phase. The result, if this happened, would be something resembling Venus at its harshest. A bare or near-bare surface exposed to a star that was, at that point in its life, even less forgiving than it is now. A secondary atmosphere is possible. Volcanic outgassing, carbon dioxide, sulfur compounds, nitrogen, can rebuild a planetary atmosphere after the primordial one is gone. Earth itself went through something like this. The question is whether Proxima b has had enough geological activity, sustained over enough time to produce a secondary atmosphere dense enough to matter. That depends on the planet's interior, its composition, its thermal history, and whether tidal forces have kept its interior warm enough to drive volcanism. None of those things are known. The geological activity of Proxima b is completely uncharacterized. Carbon dioxide and nitrogen atmospheres have something going for them that pure speculation about ozone layers does not. Research has shown that a sufficiently thick CO2N2 atmosphere can shield a planet's surface from the most damaging ultraviolet wavelengths, even without an ozone layer. The molecular absorption at certain wavelengths provides a kind of blunt force UV protection. For Proxima b, this is one of the more plausible routes to a survivable surface environment, if the atmosphere is thick enough. If surface pressures reach several times Earth's, the shielding improves substantially. Some models suggest pressures between 1 and 5 times Earth's atmospheric pressure could provide meaningful protection against the worst UV frequencies. That is the optimistic reading. The pessimistic reading is what happens over billions of years. Even a thick CO2N2 atmosphere is not a permanent structure. The relentless bombardment of extreme ultraviolet radiation and stellar wind steadily erodes the upper layers. Ions escape, gas bleeds into space. Over geological timescales, not decades, not centuries, but billions of years, even a substantial secondary atmosphere can be ground down to nearly nothing. Proxima b is roughly the same age as our solar system. It has had billions of years of this. Whatever atmosphere it had at any given point in its history has been eroding the entire time. Whether enough remains today is genuinely unknown. What makes this particularly difficult is the cascade effect. An atmosphere regulates temperature. Without one, the day side bakes under direct stellar radiation with no buffer. The night side freezes without any blanket of gas to redistribute heat. The twilight zone, that narrow ring of potentially tolerable conditions described in the previous section, exists in the models only because those models assume circulation, air moving from the hot side to the cold side, distributing energy, preventing the extremes from being quite as extreme. Remove the atmosphere, or make it thin enough that circulation becomes meaningless, and the twilight zone shrinks or disappears entirely. The one region of the planet that anyone might have pointed to as a refuge becomes just another part of a hostile face. There is something almost maddening about this uncertainty. Researchers have built detailed models of what happens to Proxima b's ozone under superflare bombardment. They have calculated ion escape rates under different assumptions about the planet's magnetic field. They have mapped temperature gradients across the day and night hemispheres. All of that work is real and valuable, but underneath all of it is this single unresolved question: is there an atmosphere? And the answer changes everything. A planet with a thick active atmosphere and a planet with no atmosphere are not two versions of the same world. They are two completely different objects, with different surface conditions, different fates, and entirely different relevance to any question about life. What astronomers do know is that the tools to answer this question may eventually exist. The extremely large telescope currently under construction and various proposed space-based instruments could potentially detect atmospheric signatures from Proxima b under the right observing conditions. Whether the geometry and contrast allow it is still being worked out. It may require multiple dedicated observing campaigns over years. The answer might come in a decade. It might take longer. For now, the question remains open in the most fundamental sense. Not open as in uncertain, but open as in completely unanswered. Every optimistic scenario for Proxima b requires an atmosphere. Temperature regulation requires it. Ozone requires it. Liquid water requires it. The twilight zone requires it. The question is not whether the planet would be pleasant to live on if it has a thick sky above it. The question is whether that sky exists. The planet might be a world with a thick sky full of carbon dioxide and nitrogen, or it might be a bare rock orbiting in vacuum, and we genuinely do not know which. The question nobody can answer about Proxima b, and the one that matters more than almost anything else, is whether the planet has a magnetic field. On Earth, this question barely registers. Our magnetic field is so woven into the conditions that made life possible that we rarely think about it. It deflects the solar wind. It bends charged particles away from the upper atmosphere before they can ionize and heat the gas that makes up our sky. Without it, the solar wind would slowly erode the atmosphere from the top down, stripping lighter molecules into space over millions of years. Mars is the case study. Mars likely had a magnetic field once. It lost it. And at some point after that, it lost most of its atmosphere too. Today, the Martian sky is less than 1% as thick as ours. The surface is bathed in ultraviolet radiation, and liquid water cannot persist anywhere on it. The magnetic field didn't just matter. It was the thing holding everything else together. For Proxima b, the same logic applies, but the numbers are in a different league entirely. Earth's magnetosphere deflects a solar wind that arrives with roughly ordinary pressure. Proxima b faces stellar wind pressures that are, in some models, more than 2,000 times higher than what Earth receives. Some of the more detailed magneto-hydrodynamic simulations push that number to 4 orders of magnitude above Earth's conditions during peak events. That is 10,000 times the pressure. A magnetic field that comfortably handles our situation would be working at an entirely different scale just to do the same job around Proxima Centauri. The question isn't just whether Proxima b has a field. The question is whether any plausible field could hold. Here is where the research delivers its uncomfortable answer. Scientists ran the simulations assuming Proxima b does have a magnetic field, an Earth-like dipole, the kind that gives our planet its protective bubble. Even in that version, even in the scenario most favourable to the planet, the atmospheric ion escape rates come out higher than those of any terrestrial planet in our solar system. Not higher than Mars without its field, higher than anything we have observed, under any conditions, across all 4 rocky worlds we can actually study: Earth, Venus, Mars, Mercury. Proxima b's best case beats the worst figures from all of them. The protection a magnetic field provides is real and significant, but the environment is so extreme that real and significant still isn't enough. Without a field at all, the picture worsens by roughly 2 orders of magnitude. Ion escape rates jump to around 100 times higher than the solar system baseline. An unmagnetized Proxima b would shed its atmosphere at a pace that makes Mars's atmospheric loss look slow. Any atmosphere that formed or reformed on the planet would be continuously shaved away from the top, lighter elements escaping fastest, the inventory of gases that matter for surface pressure and chemistry steadily bleeding into space. Over geological timescales, the word steadily is the problem. Steady erosion across billions of years doesn't leave much behind. Now there's a second layer to this. The existence of a magnetic field isn't guaranteed just because a planet has the right size or composition. A magnetic field requires a dynamo. A dynamo requires a molten conducting interior in motion, convecting, generating the electrical currents that sustain the field. Earth has this because of its internal heat, a mix of primordial warmth left over from formation and ongoing heat from radioactive decay. That interior stays hot enough to keep the outer core liquid and churning. The dynamo runs. The field persists. Tidal forces complicate this for Proxima b. If the planet's orbit has any meaningful eccentricity, the gravitational pull from Proxima Centauri flexes and compresses the planet's interior on every pass. This tidal heating pumps energy into the rock. On one hand, that sounds like it might help, like extra interior heat could sustain a dynamo more easily. But the relationship between tidal heating and magnetic field generation isn't that simple. Too much tidal heating can overwhelm the organized convection that a dynamo needs. If the interior heats unevenly or too intensely, the structured flow that generates a coherent magnetic field can break down. You get volcanism. You get a hot, churning interior. You don't necessarily get a field. Io is the extreme version of this. Jupiter's tidal grip heats Io so violently that the Moon is the most volcanically active body in the solar system, and it has essentially no global magnetic field. Proxima B's situation is more moderate than Io, but the principle applies. If the planet's orbit has even modest eccentricity, the tidal forces are working on its interior in ways that could disrupt exactly the process that would generate the field it most needs. And this happens to be the same scenario where the planet might escape full tidal locking. There is a painful irony in this. A slightly eccentric orbit means the planet rotates, which is better for distributing heat, which is better for surface conditions in some ways. But that same orbital eccentricity drives tidal heating, which threatens the dynamo, which eliminates the magnetic field, which exposes the atmosphere to the full force of a stellar wind measuring thousands of times Earth's pressure. One potential improvement trades against another. What makes this genuinely hard is that every critical variable here is unobserved. We don't know Proxima B's magnetic field strength. We don't know its orbital eccentricity with the precision needed to calculate tidal heating rates. We don't know its interior composition or whether a dynamo is running. We are not even certain whether the planet formed where it orbits or migrated inward from farther out, which would affect everything about its interior heat budget. The simulations produce answers, but every answer comes attached to a long list of assumed inputs, and the inputs are guesses. Careful, reasoned guesses, but guesses. What the simulations consistently show, across different assumptions and different teams, is that the magnetic field story for Proxima B never becomes straightforwardly good. The best available scenario is one where Proxima B has a strong magnetic field and the atmosphere is still eroding faster than anything in our solar system. The problems facing Proxima B now are serious enough, but the history of what this planet likely went through makes the current situation look almost tame. To understand why, you have to go back to the beginning, not just to the discovery of Proxima B in 2016, or even to the formation of the planet itself, but to the early life of the star it orbits. Every star, including our own Sun, passes through a phase before it settles into the stable, predictable object it eventually becomes. Astronomers call this the pre-main sequence phase. For stars like Proxima Centauri, this phase does not last a few million years, it lasts hundreds of millions. And during that entire stretch, the star is not the relatively calm, dim object we observe today. It is something dramatically more violent. The term pre-main sequence refers to the developmental stage before a star reaches hydrostatic equilibrium, the point at which the outward pressure from nuclear fusion balances the inward crush of gravity. During this transitional period, a newly formed star is still contracting and adjusting its internal structure. The gravitational collapse releases enormous amounts of energy, heating the stellar core and surrounding material. This process is not instantaneous. For massive stars, the pre-main sequence phase might last only a few million years. For smaller stars, the timeline extends dramatically. Red dwarfs, being among the smallest stars in the universe, take the longest path to maturity. Proxima Centauri, with its low mass of just 0.12 solar masses, experienced a pre-main sequence phase lasting somewhere between 100 and 500 million years, according to various astronomical models. Some estimates place it closer to 1 billion years. This extended timescale is crucial to understanding Proxima B's violent past. The reason this matters for planetary systems is fundamental to stellar physics. A young red dwarf does not simply sit quietly while it contracts and stabilizes. The internal turbulence, the ongoing gravitational reorganization, and the rapid rotation of the stellar body create conditions of extraordinary magnetic complexity. Red dwarfs are already known to be magnetically active stars throughout their lifespans, but young red dwarfs operate under magnetically enhanced steroids. The magnetic field lines that thread through the star become twisted and tangled by the roiling interior currents. These field lines store enormous amounts of energy. When they snap and reconfigure, they release that energy in dramatic fashion. This magnetic activity manifests in several observable ways. Stellar flares are among the most spectacular. A major stellar flare is essentially a magnetic explosion in the star's atmosphere. Energy released in moments can equal the total energy output of our Sun over several days. For a young Proxima Centauri, such flares were not rare occurrences separated by days or weeks. They were frequent, sometimes occurring multiple times per day. The X-ray and ultraviolet radiation produced by these flares floods outward into the surrounding space. For a planet orbiting at Proxima B's distance, which is only about 7.5 million kilometers from its star, roughly 1/20th the Earth-Sun distance, this radiation environment would be absolutely lethal by modern standards. The stellar wind compounds the problem. All stars produce a stream of charged particles flowing outward into space, carrying magnetic field lines with them. This stellar wind helps define the extent of the star's sphere of magnetic influence, a region called the magnetosphere. In our solar system, the solar wind is a gentle breeze by cosmic standards. In the early solar system, it was stronger. For young Proxima Centauri, the stellar wind was orders of magnitude more intense. The number of particles streaming outward was vastly higher. The energy they carried was correspondingly greater. Imagine standing in the path of a fire hose rather than a gentle rain. That approximates the difference between the modern Proxima Centauri stellar wind and the one that buffeted Proxima b billions of years ago. The cumulative effect on a young planet would have been extraordinary. If Proxima b possessed an atmosphere at that time, and many models suggest it may have, that atmosphere would have been under constant bombardment. Ultraviolet radiation would have broken apart atmospheric molecules, stripping away gases into space. The energetic particles in the stellar wind would have added their own erosive effect. Over hundreds of millions of years, this process could have removed an entire planetary atmosphere. A world that might have started with oceans and a protective atmospheric blanket could have been transformed into the barren, exposed world we may observe today. The rocky surface itself would have been affected. Cosmic rays and charged particles would have altered the surface chemistry and structure. Radiation would have penetrated into the upper layers of the crust, breaking down minerals and creating new compounds. The surface temperature fluctuations caused by intense stellar flares would have created mechanical stress in the rock. This is not merely damage in an abstract sense. These are processes that fundamentally reshape a planetary body. Young red dwarfs burn hot in ways independent of their surface temperature. Their magnetic fields are stronger. Their flare output is higher. The stellar wind they push outward into space is more intense by orders of magnitude, compared to what the same star produces in maturity. Our own Sun, in its early years, was far more active than it is now, and the consequences for the young Earth were enormous. Proxima Centauri's early phase was worse, much worse. The same magnetic instability that makes the modern Proxima b environment so dangerous was operating at a higher level for an extended period that, in geological terms, is almost incomprehensible in length. Set aside the numbers for a moment and try to picture what it would actually be like to stand on the surface of Proxima b. Everything you know about standing under a sky, every assumption built into that experience, would be wrong. The colour is wrong first, not subtly wrong, catastrophically wrong. Our Sun produces light that peaks in the yellow-green range, which is precisely why human eyes evolved to be most sensitive in that range. Proxima Centauri is an M-dwarf with a surface temperature barely above 3000 Kelvin. The light it throws off peaks deep in the infrared. What reaches the surface of Proxima b is dim, reddish, the colour of a dying coal rather than a burning one. If you tried to read in that light, it would feel like reading in a room where someone turned the bulbs down to almost nothing and then swapped them for red ones. The star itself would look strange. From Earth, the Sun takes up about half a degree of sky. It feels enormous when you look at it directly. Proxima Centauri, even though Proxima b orbits far closer to it than Earth orbits the Sun, would appear smaller. Proxima is only about 15% the radius of our Sun. At the orbital distance of Proxima b, that works out to a disk roughly similar in apparent size to what we see, perhaps slightly larger, but the dimness would make it feel smaller than it is. Not a blazing furnace filling the sky. a dull, sullen red eye hanging there, putting out light that barely qualifies as daylight by any standard your biology was built to expect. And it would never move. This is the part that takes real effort to imagine. On Earth, the entire rhythm of life is organized around the motion of the sun. It rises, it crosses the sky, it sets. Everything from agriculture to sleep to the structure of a day is built on that cycle. On a tidally locked world, that cycle does not exist. The star occupies one fixed position in the sky. It does not arc, it does not drift. Whatever patch of sky it sits in when you die, day is not a period of time, day is a location. If you walk toward the star, you move deeper into day. If you walk away from it, you move into darkness. The distinction between morning and night has no meaning, because there is no morning and there is no night. Stand in the middle of the day side and look up. The ground around you is lit by that flat red glow, constant and unwavering. No shadows move. Nothing changes angle. The illumination at noon looks identical to the illumination an hour later, a day later, a year later. There is no sunset coming. There is no relief from the glare, dim as it is, because the geometry of the world does not allow for it. Now look at the sky itself. If the atmosphere is thin, or mostly gone, there is no blue. The blue of Earth's sky is scattering. Sunlight bouncing off nitrogen molecules and spreading across the dome above us. Take away the atmosphere, or thin it to a fraction of Earth's, and the scattering vanishes. The sky goes black. You could be standing on a sunlit surface in the middle of the equivalent of noon, and the sky above you would look like the void of space, because functionally it is. Stars would be visible at midday, not because the star is dim enough to allow it, though it is dimmer than our sun, but because there is nothing above you thick enough to scatter its light into the rest of the dome. What about the flares? The radiation problem is the one that makes this viscerally uncomfortable to think about, because you cannot see it happening. Proxima Centauri erupts. It does this regularly. A superflare unleashes energy equivalent to what a star like our sun would take years to throw off, compressed into minutes. And the radiation from that event, the X-rays, the extreme ultraviolet, travels at the speed of light. You get no warning. One moment the star is sitting in its fixed spot in the black sky, the same dull red it always is. Then the surface of your skin is receiving a dose of radiation that would kill the hardiest organism we know of on Earth, 65 times over. You would not know it was happening in real time. There is no sound, no flash you could see with your eyes. Just energy moving through your body. Turn around and face the opposite direction. Behind you the day side stretches to the horizon. In front of you, you walk toward the terminator, the line where the lit half of the planet meets the dark half. This is the only zone where the temperature arithmetic might, under the right conditions, produce something a living thing could tolerate. The twilight band. It runs all the way around the planet like a ring, a narrow strip of permanent near dusk where the star sits at the horizon and never drops below it, never rises above it. The light here is even dimmer than on the full day side, which was already barely enough. It has the quality of the last few minutes before complete darkness on Earth, except it never gets darker and it never gets brighter. Perpetual late evening, lit in red. If there is enough atmosphere to move heat around, this band might stay liquid. Temperatures that do not freeze and do not bake. The only place on the entire planet where you could, in theory, be without a suit that protects you from vacuum on one side and temperatures of negative 120 degrees on the other. Step past that line, walk into the night side. The star disappears below the horizon immediately and does not come back. The temperature drops. It keeps dropping. The night side of Proxima b, permanently shielded from any stellar warmth, hits temperatures around negative 123 degrees Celsius. Colder than anywhere on Earth's surface. Cold enough that carbon dioxide itself would freeze out of the air. If there is any air, there is no starlight here bright enough to navigate by easily. No moon has been confirmed in this system. The darkness is total, the cold is structural, and nothing in that hemisphere has seen direct light from its star since the planet locked into this orientation billions of years ago. Think about what weather looks like, if it exists. On Earth, weather is driven by differential heating. The sun warms the equator more than the poles. It warms land differently than ocean. It warms the day side while the night side cools. All of those gradients drive motion in the atmosphere. On Proxima b, if there is an atmosphere, the gradient is the most extreme version of any terrestrial planet we know of. Boiling heat on one side, deep freeze on the other, a permanent circulation driven not by the daily rotation of a planet, but by the fixed wall of temperature between two hemispheres. Any wind that exists would be a relentless one-directional pressure, hot gas pushing from the day side toward the cold, cold air pushing back. Not seasons, not storms that build and pass. A permanent atmospheric engine, driven by a temperature difference that never changes, because the geometry of the planet never changes. There would be no rain cycle in any sense you would recognize, because rain requires a water cycle, which requires liquid water moving between surface and sky. If there is water at all, and that is itself uncertain, it would be frozen solid on the night side and potentially vapor on the day side, with any liquid confined to that narrow terminator band, if conditions allow it, and if the atmosphere is thick enough to maintain the pressure needed to keep water liquid at the surface. What would the psychological experience of this be? You can ask the question even if it is purely hypothetical. The feature of Earth's sky that anchors all of human experience, in every culture, in every century, is that the sky moves. The sun traces its arc. The stars rotate around fixed points as the night goes on. The moon rises and sets. Everything moves. On Proxima b, none of it moves. The star is fixed. Any other stars visible in that black sky would slowly wheel around it over the course of the planet's 11-day orbit, but the star itself, the only source of light, would be locked to its position as certainly as a painted point on a ceiling. Every hour of every day you are alive on that surface, the star would be in exactly the same place. The star would never move, never set, never rise, just hang there in the same patch of sky, dimly burning, for as long as you lived. Proxima b is not alone in its system, and the other objects orbiting Proxima Centauri make an already complicated picture more complicated still. For most of the years following the 2016 announcement, the public conversation treated Proxima b as a solitary world, one star, one planet, one question. That framing was always too clean. Radial velocity measurements, the technique that detects planets by watching how their gravity causes a star to wobble slightly as they orbit, had been accumulating data on Proxima Centauri for years. When researchers looked carefully at the numbers, a second signal emerged. Something with a mass somewhere between 6 and 7 times that of Earth appeared to be orbiting Proxima on a cycle of roughly 5 years. Farther out, slower, much larger. And then, at the other end of the scale, a third candidate turned up even closer to the star than Proxima b itself, a sub-Earth with a mass around a quarter of our planet's completing its orbit in just a few days. So the system has at least 2 other objects, possibly more, and they are not sitting quietly in the background. The 6 to 7 Earth mass planet is the one that matters most for Proxima b's situation. An object that size, orbiting on a 5-year cycle, exerts real gravitational influence on everything inside its orbit. Gravitational interactions between planets are not static. Over millions and billions of years, they nudge each other. They pump energy into orbital paths. They can slowly push a nearly circular orbit into a more elongated one. For Proxima b, that nudging has a specific consequence that pulls in 2 directions at once. A more elongated orbit, higher eccentricity in the technical language, might actually rescue Proxima b from full tidal locking. If the eccentricity climbs above roughly 0.06 to 0.1, the planet could fall into a 3 to 2 spin-orbit resonance instead. That is the same configuration Mercury is in, 3 rotations around its own axis for every 2 orbits around the star, A day on Proxima b in that scenario would last about 7.5 Earth days. Not ideal, but better than permanent noon on one side and permanent midnight on the other. Some researchers have pointed to this possibility as a narrow path towards slightly more manageable surface conditions. The problem is that higher eccentricity comes with a cost. When a planet's orbit is elliptical rather than circular, the varying distance from the star creates tidal flexing in the planet's interior. The rock itself bends slightly as the gravitational pull strengthens and weakens. That flexing generates heat. Io, the closest of Jupiter's large moons, has the most volcanically active surface in the solar system precisely because of this effect. Jupiter's gravity kneads it constantly as it moves through its orbit. For Proxima b, stronger tidal heating from a more eccentric orbit could push volcanic activity to extreme levels. That kind of internal chaos does not necessarily help a planet retain a stable magnetic field. The same dynamics that could free the planet from tidal locking might simultaneously undermine the magnetic field, protecting it from stellar wind. The two things that look like they could help are connected in a way that means you may not be able to have both. Then there is Alpha Centauri. Proxima Centauri is gravitationally bound to a binary star system, Alpha Centauri A and Alpha Centauri B, roughly 0.2 light-years away. That is an enormous distance by human standards, but in orbital mechanics terms, a gravitational connection across 0.2 light-years, maintained over billions of years, is not nothing. The binding is loose. Proxima orbits the Alpha Centauri pair on a cycle that may take millions of years to complete. Over those timescales, the influence of two other stars on the system is not completely negligible. Perturbations accumulate slowly. They can shift orbital parameters in ways that compound over geological time. Exactly how much this has affected Proxima b is not known with precision, but adding two additional stellar masses to an already complicated multi-planet gravitational environment does not simplify the picture. The sub-Earth at the innermost orbit is less understood. Its mass is small enough that it does not exert the same gravitational leverage as the outer planet, but its existence is a reminder that the Proxima system is dynamically active. Planets formed there, orbits evolved, interactions happened. A system that produced multiple planets at radically different sizes and orbital distances has had a complex history. That history is written into the current orbital architecture, and reading it accurately requires more data than anyone currently has. What all of this adds up to is a system that resists simple conclusions. The single planet model, where Proxima b sits alone in its orbit, and the only variables are its relationship with the star, was always a simplification. The actual gravitational environment includes at least two other bodies with real influence on the planet's orbital shape, its internal heating, and potentially its magnetic field. Each of those influences, when traced through what they mean for surface conditions, tends to push things in a direction that is harder rather than easier. A more eccentric orbit raises tidal heating. More tidal heating complicates the magnetic dynamo. A disrupted magnetic field accelerates atmospheric loss. The chain of consequences does not terminate somewhere comfortable. Every layer of complexity added to the Proxima system introduces new ways for the planet's already marginal conditions to be pushed further toward the uninhabitable end of the spectrum. The models of Proxima b's climate do not agree with each other, and the disagreements are not small. When researchers try to calculate the temperature on the day side of Proxima b, they get answers that vary by dozens of degrees depending on what they assume going in. Some studies put the maximum dayside temperature at around 235 Kelvin, which is roughly minus 38 degrees Celsius. Others push that number up to 300 Kelvin, which is about 27 degrees Celsius, warm enough for liquid water. That is a 65-degree spread between studies that are all, technically, trying to model the same planet. The reason for the gap is not that the scientists are making mistakes. The reason is that nobody knows the actual values of the parameters that drive the model outputs. Take atmospheric pressure. An atmosphere at 100 millibars behaves completely differently from one at 5,000 millibars. A thin atmosphere circulates weakly, traps little heat, and leaves the night side in a deep freeze. A thick atmosphere redistributes heat more efficiently, keeps the night side from collapsing into a cold trap, and raises the average surface temperature across the planet. Models that assume a thick atmosphere produce results that look more hospitable. Models that assume a thin one produce a world where the night side drops to around 150 Kelvin, roughly minus 123 Celsius, cold enough to freeze carbon dioxide out of the air entirely. Neither assumption has been confirmed by observation. Researchers pick a pressure, run the model, and report what comes out. Surface albedo is another lever that swings the results dramatically. Albedo is a measure of how much incoming light a surface reflects. Earth's bond albedo sits around 0.3, meaning we reflect about 30% of the solar energy that hits us. If Proxima b has a high albedo from ice cover or thick clouds, it reflects more energy back and stays cooler. If it has a low albedo, dark rock or deep ocean, it absorbs more and warms up. The difference between a high albedo and low albedo Proxima b, all else being equal, is the difference between a frozen world and a marginally temperate one. And the albedo of the planet is entirely unknown. Oceans matter enormously in these models as well. Water has a high heat capacity. It stores thermal energy and releases it slowly. An ocean-covered Proxima b would buffer temperature swings between day and night, potentially moderating conditions across the terminator zone. A dry, rocky Proxima b would show far more extreme contrasts between illuminated and dark hemispheres. Whether the planet has surface water at all is one of the central open questions, and the early history of the system, the period when young Proxima Centauri was at its most violent, suggests the water budget of the planet may have been devastated long before any climate we are modeling could have developed. Volcanic activity introduces yet another unknown. Active volcanism can replenish an atmosphere that is being stripped by stellar wind and radiation. It can inject carbon dioxide and water vapor into a thin atmosphere, gradually rebuilding surface pressure over geological time. Some scenarios for a habitable Proxima b depend heavily on the planet maintaining a volcanic outgassing rate high enough to keep pace with atmospheric loss. Whether that rate is sufficient is something no model can currently answer from first principles, because we do not know the planet's internal structure, its tidal heating rate, or its geological age in any meaningful sense. What happens when you stack all of these uncertainties together is that the models split into two camps, and neither camp is reassuring. The pessimistic models, those that assume thin or absent atmospheres, low volcanic replenishment, and unshielded stellar wind exposure, produce a world that looks like a smaller, more irradiated version of Mars. Bare rock, no liquid water, a surface sterilized by radiation and blasted by charged particles, with no ozone layer and no magnetic protection worth mentioning. This version of Proxima b is not a borderline case. It is simply dead. The optimistic models are more interesting and more carefully constructed. They assume a thick atmosphere, active volcanism, sufficient surface pressure to drive circulation, and a magnetic field strong enough to reduce atmospheric erosion to manageable rates. Under those conditions, climate simulations do produce a narrow habitable zone at the terminator. Temperatures in this twilight band sit somewhere between -30 and +30 Celsius. Liquid water becomes theoretically possible. The model looks, at a distance, almost encouraging. But read the assumptions list carefully. Thick atmosphere, unconfirmed. Active volcanism, unknown. Sufficient magnetic field, entirely unobserved. Atmospheric composition favorable for greenhouse warming, speculative. Albedo in a range that supports moderate temperatures, a guess. Each one of those conditions has to be true at the same time for the optimistic picture to hold. Remove any single item from the list and the conclusion changes. Take away the magnetic field and atmospheric loss rates, jump to levels that no volcanic outgassing is likely to offset. Take away the thick atmosphere and the terminator zone collapses into temperature swings too extreme for liquid water to persist. Adjust the albedo upward and the day side cools past the threshold where circulation can keep the night side from freezing solid. No published model has produced a habitable Proxima b without requiring several of these favourable conditions simultaneously. And this is not a criticism of the modelling work, which is genuinely sophisticated and careful. It is simply what the physics demands. The planet sits in a location where the margins are razor thin and the unknowns are enormous. Every version of Proxima b that looks even marginally habitable requires a long list of things to be true simultaneously, and we have confirmed none of them. There is a reason Proxima b keeps appearing on lists of potentially habitable worlds, despite everything working against it. That reason is not the science. The science, taken honestly, does not support easy optimism. The reason is distance, or rather the lack of it. At 4.2 light-years away, Proxima b is the closest exoplanet that will ever exist in any practical sense. No matter how many other planets get discovered around other stars, no matter how many candidates turn up in habitable zones scattered across the galaxy, this one will always be the nearest. That fact alone changes how people write about it. It changes what questions get asked and, more importantly, which answers get emphasized. There is a term for this in research, selection bias, but the version playing out with Proxima b is subtler than the textbook definition. Scientists studying the planet are not being dishonest. The papers are careful. The caveats are there, buried in the methods sections and the discussion paragraphs, where they belong. A study modelling atmospheric survival under optimal conditions will note, somewhere in its text, that optimal conditions are assumed. It will flag the uncertainties. It will be precise about what the model does and does not demonstrate. Then the press release goes out. Then the headline runs, the assumptions get dropped, the caveats vanish. What reaches the public is something much simpler and much more exciting than what the researchers actually concluded. And once that version of the story circulates widely enough, it becomes the default framing, the thing everyone already knows, the background assumption that the next round of coverage builds on without re-examining. This happened with Betelgeuse in late 2019 in almost exactly the same way. A star was dimming. Astronomers had genuine uncertainty about the cause. The actual scientific conversation was cautious, full of competing hypotheses, and far from settled. None of that complexity survived contact with a headline. What the public got instead was a countdown. The star might explode tomorrow, tonight, any moment now. The drama was real, the uncertainty was real, but the specific conclusion the coverage pushed was not supported by what the data actually showed. When the star brightened again a few months later, the story moved on, and most people never encountered the far stranger and more interesting truth that took years of careful observation to unravel. The headline served its purpose and left the science behind. Proxima b has been living inside a version of that same cycle since 2016. The discovery announcement was legitimate and significant. A roughly Earth-mass planet orbiting in the habitable zone of the nearest star. That is genuinely extraordinary. Nobody fabricated the finding, but the phrase habitable zone did an enormous amount of work in those early headlines, carrying implications it was never designed to carry. The habitable zone is an energy budget calculation. It says nothing about magnetic fields. It says nothing about stellar flares. It says nothing about tidal locking or atmospheric stripping or the violent early history of a red dwarf system. The habitable zone was built as a first filter, a rough cut for identifying candidates worth examining further. It became, in popular coverage, something closer to a certificate, and Proxima b, being the closest candidate on the list, collected that certificate first and most visibly. The consequences of this are not just about public perception. Framing shapes funding. It shapes which missions get proposed, which telescope time gets allocated, which questions get treated as settled, and which get treated as open. When a planet is understood by policymakers and program directors as a promising habitable world, rather than as a scientifically extreme environment full of unresolved problems, the research priorities that follow are different. That is not an abstract concern. The James Webb Space Telescope cannot observe Proxima b directly. The geometry does not allow it. Future missions that could probe the planet's atmosphere will require specific justifications, specific framings of what is being tested and why. Whether those missions get built depends in part on whether the people controlling resources understand that the atmosphere question is genuinely open, not already answered in the affirmative by a decade of optimistic coverage. None of this means Proxima b should stop being studied. The opposite is true. A planet this close, presenting this many extreme conditions simultaneously, is an extraordinary scientific object. The radiation environment alone makes it one of the most intensely studied exoplanet cases in the literature. The tidal locking problem, the stellar wind problem, the ozone destruction cycle, each of these is a live research question with implications far beyond this single planet. Proxima b is the sharpest test case available for every theory about how red dwarf planets retain or lose their atmospheres, how magnetospheres respond to extreme stellar wind pressure, how flares interact with planetary chemistry over geological time. Those questions are genuinely important. The answers will apply to thousands of planets around hundreds of red dwarfs. Proxima b is not valuable because it is probably habitable. It is valuable because it is the closest place to run the experiment. What it deserves, then, is not cheerful framing designed to maintain public enthusiasm, and not dismissive framing that treats it as already ruled out. It deserves precision. It deserves coverage that holds the uncertainty exactly where the research holds it. The models disagree. The atmosphere may not exist. The magnetic field status is unknown. The flare frequency is documented and brutal. These are not caveats to be mentioned briefly before returning to the exciting possibility. They are the actual state of the science, and they are interesting in their own right. A world this difficult to make work as a home for life is not a disappointment. It is one of the most scientifically interesting objects within reach, and it deserves the honest version of its story. A single observation that would change the entire conversation about Proxima b is one nobody has made yet. No telescope currently operating has detected an atmosphere around this planet. Not a thin one, not a thick one, nothing. Every argument made about what might protect the surface, what might regulate its temperature, what might allow liquid water to pool somewhere in that narrow twilight band, all of it assumes something exists that has never been confirmed. The next real chapter in this story depends on instruments that are either just coming online or still being built. The extremely large telescope, currently under construction in Chile's Atacama Desert, is the most credible near-term candidate for changing that. Its primary mirror stretches nearly 40 meters across. That is not an incremental upgrade over existing observatories. It is a fundamentally different class of instrument. The light-gathering power it brings to bear on faint signals from nearby exoplanets puts atmospheric detection within range for the first time. Proxima b, at 4.2 light-years, is the closest target astronomers will ever have. If any ground-based telescope can pull an atmospheric signal from this planet, the ELT is it. Several proposed space missions are also being designed with exactly this kind of detection in mind, though timelines and funding for those remain uncertain. What the detection itself would actually require is worth understanding. Proxima b does not transit its star from Earth's perspective, which rules out the most common method astronomers use to read exoplanet atmospheres. Transit spectroscopy, watching starlight filter through a planet's atmosphere as it crosses in front of the star, is how most atmospheric detections have happened so far. Proxima b's orbital geometry doesn't cooperate. Instead, astronomers would have to use direct imaging techniques combined with high-resolution spectroscopy, essentially trying to separate the planet's faint reflected light from the overwhelming glare of the star next to it. This is extraordinarily difficult. The star outshines the planet by a factor that makes the problem resemble trying to see a firefly hovering next to a searchlight from several kilometers away. If that signal is ever extracted, the first thing it would tell researchers is whether any atmosphere exists at all. That alone would be significant. Just knowing the planet has air, any air, would confirm that something survived the early bombardment, that the stellar wind hasn't stripped everything away, that there is at least a starting point for the rest of the questions. Then comes the composition. A thick carbon dioxide and nitrogen atmosphere would look very different from an Earth-like mix of nitrogen and oxygen. CO2 has distinct spectral fingerprints. So does water vapor. So does methane. The pattern of absorption lines in the reflected light would tell researchers what molecules are present and in what rough proportions. Here is where things get complicated. Oxygen is considered one of the strongest biosignatures. On Earth, it is almost entirely produced by living things and would disappear from our atmosphere within a few million years without biological replenishment. Finding oxygen in a planet's atmosphere is, in most contexts, a striking signal. On Proxima b, it might mean nothing of the kind. The radiation environment around Proxima Centauri is intense enough to drive photochemical reactions in the upper atmosphere that produce oxygen abiotically. Ultraviolet radiation hitting water vapor or carbon dioxide can split those molecules and leave oxygen behind without any biology involved. This is called abiotic oxygen production, and it is a known false positive risk for any planet orbiting an active red dwarf. Detecting oxygen on Proxima b would not be a discovery of life. It might simply be a record of the radiation doing what it always does. Ozone presents the same problem. On Earth, ozone is a product of oxygen, which is a product of photosynthesis. Finding ozone feels like finding a biological chain of causation. Around a star like Proxima, ozone can also form through radiation chemistry, and its presence or absence would reflect the balance between production and destruction by flares rather than anything biological. The same star that makes the surface difficult for life to occupy also makes the atmospheric chemistry difficult to interpret. Researchers studying this exact problem have flagged it clearly. Biosignature gases that look unambiguous around Sun-like stars become deeply ambiguous around M dwarfs, because the radiation environment produces them through non-biological pathways. Methane is slightly different. Methane in combination with oxygen is a stronger biosignature because the two gases destroy each other chemically and should not coexist without a continuous source replenishing both. If Proxima b's spectrum showed methane and oxygen together, that would be harder to explain abiotically. But detecting methane at that level of precision, for a planet this far away and this difficult to image directly, is beyond what near-term telescopes can deliver. The easier detections come first. Carbon dioxide, water vapor, the broad outlines of atmospheric pressure, those are the initial targets. The subtle combinations that would actually suggest biology are further down a very long road. What a confirmed atmosphere would actually mean in practical terms is that one item gets crossed off a list that still has many items remaining. It would not answer whether the surface temperature is tolerable. It would not answer whether liquid water exists. It would not answer whether the ozone problem has somehow been solved, or whether flares are stripping the air faster than any process replenishes it. It would not come close to answering whether anything lives there. What it would do is establish that the planet is worth the next level of scrutiny, that the conversation can move forward rather than stalling permanently at the question of whether there is anything to study. That gap between what detection would prove and what the headlines would almost certainly claim is worth holding in mind. The pattern has repeated before with this planet. Discovery announcements ran ahead of the careful findings. The habitable zone designation got treated as near confirmation of habitability. An atmospheric detection, if it comes, will face the same pressure. The signal will be weak, the interpretation will be contested, and the actual scientific conclusion will be far more cautious than whatever phrase trends that week. Before anyone can seriously ask whether something lives there, the first question, does the planet even have an atmosphere, is still completely open. Proxima b is the most studied example of a planet type that, statistically, should be everywhere. Red dwarf stars make up roughly 3/4 of all stars in the Milky Way. That is not a small fraction. That is the dominant class of stellar object in the galaxy, outnumbering everything else combined. And because red dwarfs are so dim, their habitable zones sit close in, where small rocky planets form easily and frequently. The result is that when astronomers survey exoplanet candidates orbiting in habitable zones, a disproportionate number of them orbit red dwarfs. Proxima b is not an outlier. It is the nearest member of the most common category of potentially habitable world we know about. This is where the numbers start to feel significant. If red dwarf habitable zone planets are genuinely habitable, then the galaxy is almost certainly full of life. The math is straightforward. Billions of red dwarfs, most of them hosting at least one rocky planet in the right orbital range, across a galaxy that has been running this experiment for 10 billion years. The conclusion seems almost inescapable. Some researchers have looked at these numbers and argued that if life can survive on worlds like Proxima b, then the probability of finding it somewhere nearby is high enough to be genuinely exciting. That argument rests on a single load-bearing assumption that being in the habitable zone is enough. The TRAPPIST-1 system became one of the most discussed discoveries in recent astronomy for exactly this reason. In 2017, researchers announced that a small red dwarf about 39 light-years away was hosting 7 rocky planets, and at least 3 of them sat in the habitable zone. Headlines ran immediately. 7 worlds around a single star, 3 of them potentially capable of holding liquid water. It felt like confirmation that the galaxy was packed with opportunity. What the headlines moved past quickly was that TRAPPIST-1 is an even more active flare star than Proxima Centauri. The innermost planets receive radiation doses that would strip atmospheres on geological timescales measured in millions of years, not billions. Even the outer habitable zone candidates face tidal locking, intense XUV bombardment, and the same atmospheric loss questions that haunt Proxima b. The system was genuinely remarkable. The habitability framing was genuinely premature. LHS 1140b gets discussed as one of the more promising red dwarf candidates because it orbits slightly farther out, and its host star appears somewhat less active than Proxima. Astronomers detected hints of a nitrogen-rich atmosphere in 2024, which generated real excitement. But LHS 1140 is still a red dwarf. Its habitable zone planet still sits at a fraction of the distance Earth orbits the Sun. The radiation environment is still fundamentally different from what Earth experiences. The hints of atmosphere are exactly that, hints, not confirmation, not characterization. Ross 128b is another example. Orbiting a relatively quiet red dwarf for about 11 light-years away, it attracted attention partly because its host star flares less frequently than Proxima. Less frequently, though, is not the same as safely. The baseline XUV irradiance on close inhabitable zone planets does not depend on flare frequency alone. It reflects the ordinary, constant output of the star, and that output is structurally elevated for any planet close enough to receive habitable zone levels of warmth from a dim red dwarf. Here is the problem at the center of all of this. The habitable zone was not designed with red dwarfs in mind. The concept was developed by astronomers studying sun-like stars, specifically the narrow range of orbital distances where a planet like Earth, with an atmosphere like Earth's orbiting a star like the Sun, could maintain liquid water on its surface. Those 3 conditions, Earth-like planet, Earth-like atmosphere, Sun-like star, were built into the concept from the start. They were the assumed defaults. When researchers began discovering planets around red dwarfs and placing them on habitable zone diagrams, they were applying a framework built for one kind of stellar environment to a categorically different one. The orbital distance calculation still works. A planet at 0.048 AU from a star as dim as Proxima does receive roughly the right amount of total energy to keep water liquid. Assuming everything else is equal. Everything else is not equal. The radiation spectrum is different. The stellar wind is different. The flare frequency is different. The tidal dynamics are different. The early stellar evolution history is different. Red dwarfs spend hundreds of millions of years in a pre-main sequence phase that is dramatically more violent than anything a sun-like star produces. And they do this precisely when any nearby planet would be trying to hold onto a primordial atmosphere. A rocky planet forming around a red dwarf spends its early history in conditions that would strip it bare long before the star settles down. By the time the star becomes the relatively stable object astronomers observe today, the planet has already been through an ordeal that sun-like habitable zone planets never face. The habitable zone diagram does not capture any of this. It shows you where liquid water might exist. It does not show you what the planet survived to get there. What makes this more than an academic point is the scale. If the habitable zone around a red dwarf is a systematically misleading concept, if it reliably identifies planets that look promising on paper but face conditions that make surface life nearly impossible in practice, then the most commonly cited pool of potentially habitable worlds in the galaxy is the wrong pool. Researchers have used the frequency of red dwarf habitable zone planets to argue that life should be common in the universe. Those frequency arguments assume the planets in question can actually support life. Pull that assumption out, and the statistical case collapses. The galaxy may still be full of potentially habitable zone planets around red dwarfs. They may simply not be habitable. This matters for how resources and telescope time get allocated. Missions designed to characterize exoplanet atmospheres are expensive and limited in number. If the scientific community is prioritizing red dwarf habitable zone planets because they are common and nearby, and if the environment around red dwarfs systematically undermines the conditions those planets need, then the search is being directed at targets that are selected for proximity rather than genuine promise. The counter-argument is that proximity is a real scientific advantage. Proxima b and the TRAPPIST-1 worlds are close enough to actually study, which is why they dominate the conversation. You look where the light is good enough to see by, but looking where the looking is easy and looking where life is likely are not necessary. You look where the light is likely are not necessarily the same direction. None of this rules out life on red dwarf planets. Subsurface oceans, underground ecosystems, organisms with radiation tolerances beyond anything on Earth, these remain possible. Life is more stubborn than any single model gives it credit for. But surface habitability, the kind implied by the phrase habitable zone, requires a specific set of conditions that red dwarf planets appear uniquely ill-suited to maintain. The zone exists. The conditions that make a zone habitable may not. If the habitable zone concept breaks down around red dwarfs, and the evidence increasingly suggests it does, then the most common planets in the galaxy's habitable zones may not be habitable at all. On a clear night, from anywhere on Earth, you cannot see Proxima Centauri. The closest star to our Sun is too dim, magnitude 11.1, far below the threshold the human eye can detect. You need a telescope just to confirm it exists, and even then it looks like almost nothing, a faint red point in the southern constellation Centaurus, unremarkable in every visible way. The star 4.2 light-years away, the nearest stellar neighbor humanity has ever had, is completely invisible from the surface of the world that has spent decades wondering if something lives near it. Proxima b is even harder to see. It orbits a star we cannot see with the naked eye, at a distance so close that its entire year takes 11.2 Earth days to complete. No telescope currently in operation has photographed it directly. No instrument has measured its atmosphere. The planet that captured global headlines in August 2016 remains, in every practical observational sense, completely hidden. What we know about it comes from the wobble it induces in its star's radial velocity, a faint gravitational signature, not an image, not a spectrum, not a measurement of anything on the surface itself. The light reaching Earth from Proxima Centauri tonight left the star 4.2 years ago. Whatever the star was doing in that moment, whatever flares it launched, whatever it was putting Proxima b through, That information is still in transit. The planet has completed roughly 138 orbits of its star since that light began crossing the gap between us. 138 years in Proxima b terms. All of that happened before the light we're receiving now even arrives. What we are left with is a planet that may be a bare, stripped rock orbiting in near vacuum, scoured clean by stellar wind long before any life had a chance to form. Or it may have held on to something. A thin atmosphere, a narrow band of twilight temperatures, enough pressure at the surface to keep liquid water from immediately boiling or freezing solid. Nobody has ruled out either version. Nobody has confirmed either version. The range of what Proxima BC could be stretches from dead silence to something barely precariously possible, and nothing in the data yet narrows that range to a definitive answer. What is certain is the environment surrounding it. The flares are real. The XUV irradiance, 60 times Earth's, is real. The stellar wind pressure is real. The tidal locking mechanism is real. The early history of the star, that violent pre-main sequence phase when Proxima was pouring out radiation at rates far above its current levels, stripping whatever primordial atmosphere the planet had managed to accumulate. That sequence of events almost certainly happened, whether or not anything remains today as evidence. The physics doesn't require confirmation, it just requires time. The honest picture of Proxima b, assembled from a decade of careful research, is of a world stacked against itself from nearly every angle. The star is the wrong kind, the orbit is the wrong distance, the radiation environment is the wrong intensity, the locking mechanism removes what a planet needs to distribute heat. The stellar wind pressure tests whatever magnetic protection the planet might have managed to generate. Each problem on its own might be survivable. Together, they describe something that looks less like a second Earth, and more like a reminder of how specific the conditions here actually are. The universe is not particularly interested in making things convenient. The closest star to Earth happens to be one of the most hostile. The closest exoplanet in the habitable zone happens to face conditions that challenge every definition of that phrase. The most accessible target for future atmospheric studies happens to be the one where a confirmed detection of air would still only be the beginning of a very long list of other questions. Proxima b keeps orbiting, 11 days to a year, one side always burning, and one side always frozen, waiting for us to build something powerful enough to see it clearly.